So, yeah, my job now is to talk about the future. So Rodri made a good job explaining you what the present is, and the present for us is always what has been approved by the relevant bodies, and then we can work on it. So now I'm going to try to explain you that recently we've got many new requests from different sides of the experiments community, high energy experiments, low energy experiments, and some more that are coming like from you yourself, as I hear. So I try to explain you what are we doing about it and how can we deal with all these requests. And first, I will start introducing you the CERN Accelerator Complex, because we have basically two complexes, one for protons and one for ions. And this is highlighted with the green light here. So we have our source that goes through the LINAC-3 linear accelerator. And then the beams, the ion beams are injected into LEAR, the low energy ion ring. These small numbers tells you when the machine entered in operation for the first time. And in parentheses, you have the circumference of the machine. So from the LEAR, we take out these ions to have further acceleration stages. So next one is the PS. We don't use the booster. In fact, LEAR is doing the job of the booster. Booster is for protons, LEAR is for ions. And then when these ions cannot be accelerated anymore, we throw them to the next machine, which is the SPS. And here we have two injection lines into the LAC. One is for this beam, which is beam 2, by the way, is the anti-clockwise beam, and beam 1 is going through this path, and this is the clockwise beam, and they collide at the different interaction points to give these nice luminosities that Rodri told you before. I like to say that not only LAC is doing physics with ions, also in the SPS, we have two experiments, NA61 and NA60, that are using our ions. And in PS, in the east area, we have also radiation facilities using the ions from our injector complex. So a little bit more detail, and I focus on the lead operation because it has been the ion species requested by the experiments long ago for doing the LAC physics, and that was the only ion they wanted. So we had to design this ion complex based on this unique request. And so what we have is we use, in order to produce the lead beam, a small sliver of solid isotopically pure lead-208, which is placed in a ceramic crucible, and this sits in an oven. And you can see here all the source. This is our ion source and our ion expert, Detlef. And this is electron cyclotron resonance ion source installed in 2005. We had other ion sources in the past doing also different ion species, but for other programs like the SPS North Area Physics, for example. So the metal is heated around 800 degrees and ionized to become a plasma. And then the ions are extracted from the plasma and accelerated to 2.5 kilo-electron volts per nucleon. This is working on pulse operation in afterglow mode, and it produces millisecond-long pulses at 10 hertz, but we only chop 200 microseconds pulses out of it, and those are the ones accelerated and sent to the LINAC-3. The source is equipped with gas injection because on top of lead, we can do other ion species. And what is rather easy for us to do is gases. And that's why we use this gas injection mechanism. And there are two micro ovens. So this source can also run other species. And we hope next year to do the oxygen, though it was already done in 2005. Argon has been sent to the NA61 experiment, and xenon has been sent to NX61 and LAC as well in the past. So the source is here inside this cage, surrounded by these fences in blue, and the beam comes, the lead beam comes at 2.5 kiloelectron volts per nucleon with several charge components. So this spectrometer selects the lead 29 plus, and then the beam goes up into the slide via an RFQ and a series of Alvarez structures that will bring the beam to 4.2 megaelectron volts per nucleon until the beam finds a stripper foil that will strip the beam to lead 54 plus. And this is what is sent to Lear, the next machine. So as you can see in this slide, the hole, just one single hole, contains all power systems and all accelerator equipment. Therefore, during operation of the ions, in this particular case, the lead, access sometimes is required, and we are allowed to access the hole during the machine operation. But at the same time, this creates limits for radiation, which are due to the source X-rays production, so the source itself. The radio frequency cavities also emit X-rays, and there is also neutron production from some elements, not from lead, but some light ions, like in the case of the oxygen, they produce more neutrons that we have to deal with.
Can I ask a question?
Yes, sure.
So this is this ion source. I mean, just hypothetically, what it takes to add another independent ion source? Like, what's the cost and how difficult it is to put this together with the,
Yeah, so that's a very good question. And as you will discover along the talk, this is one of the questions that we will have to answer during the next months. And there is a working group working on this. So I don't have an answer today. I don't know, I guess some couple of millions or maybe more. But you see, there is not only a second source needed, we need the space. Here in the picture, you cannot have a very good feeling, but if you are inside this hole, there is not much space left to put a second ion source. So all these considerations make a second ion source something rather expensive, but okay. We will have to answer this question properly in the few coming months. So the next machine is the low energy ion ring. And this is a machine of around 80 meters. It's a synchrotron, 80 meters circumference. Lear, the low energy ion ring, accumulates the 200 microseconds pulses from the LINAC 3. Then it bunches them in 1, 2, or 3 bunches, depending on the functionality that we want to do afterwards. There is this, we have an electron cooling system. Here it is in this section of the machine with the 2 towers for the electron injection. Then the beam meets the ion beam and then it's collected here. It's used to cool down our ion beam for the required brightness. And then the beam is finally accelerated to 72 megaelectron volts per nucleon in the case of lead. For other ion species, the kinetic energy at extraction is different, of course. Then the beam is transferred to the PS, and this process takes 2.4 seconds or 3.6 seconds, depending on if we do 7 injections. So 1, 2, 3, you can count them. There are 7 injections here. Each injection is 1 pulse of 200 microseconds from LINAC 3. Then we cool the beam during all this process in order to keep the emittance down and fight a space charge. And when the accumulation is over, we switch off the electron cooling we switch on the RF system, we capture in 2 bunches, and then we start acceleration. You see in black the magnetic field of our main magnets, and the beam here is extracted to the next machine. This is what we do with the beam that goes to LAC, because they require the highest brightness possible, so intensity versus emittance. However, NA61 is not demanding on intensity, so they have enough with just a single injection from LINAC 3, and this is what you see here. This is the cycle we use for filling the beam in SPS for NA61. All right, so the next step is to go to the PS, but there are no many constraints. And then the next step will be to go to the SPS. And as Roderick mentioned before, there we do a slip stacking for the LAC beams only, not for NA61, okay? And then the beam goes to LAC. So having saw a little bit how our injector complex looks like, I would like now to go to tell you what are the requests that we've got for RAM4 and beyond. Is there any question? No? All right, so in RAM4, we have the following requests. NA61, which is a quark gluon plasma experiment, trying to understand the onset of fireball, is willing to have 4 runs with 4 different species per run. And these species can be either for the low mass lithium, helium, or boron to be seen. We have to find out what is the best from the accelerator complex point of view, because from the physics point of view, for them, this is similar. So we will always take the one that is easier for us to operate. And magnesium, oxygen, and argon. So in red, there are the elements that we haven't done before, that we don't know yet how to operate. And in green are the elements that we have some experience already. At the same time, NX60++, which is a QCD experiment, is willing to go on with lead beams in RAM4. And at the same time, LAC is willing to go on with lead during RAM4. Okay, so you see already, if you remember my slide before with the source, there is only one source. This is going to be, you feel it already, it's going to be very complicated to serve so many requests with only one source and one LINAC.
So for the ion, if one are interested in a particular isotope, stable isotope, would that have any difference from the source point of view? Like you want some.
No. So
abundance you need to. It's easy. I mean, the cost of getting, let's say, pure source of particular isotope, is this the cost compared to the rest? Is this a major cost or
so we always try to use the most abundant isotopes and highly pure, as I said at the beginning. But because for the experiments that we have today in front, NA61, NA60, and LAC, they don't care about variant 1-2 nucleons difference in the mass. Okay, that's fine. But if there is a request on a particular isotope, which is more rare, the only problem will be that will become much more expensive. So the bill that we have to pay will be higher. Right. But from the technical point of view, not. Although it might be a problem if this rare isotope comes with high contamination. These the experiments don't want either. So it will be a balance.
But the cost of the, I mean, the LHC is always cost a lot of money. So I don't know, getting a particular isotope which the abundance is not very high. I don't know, like, is this a major cost compared to the rest?
No, it not. So the cost of the isotope is not driving the decision, because the full program is much more expensive than the cost of the rare isotope.
Thank you.
All right, so round 5 and round 6 requests, and I like to emphasize here that all these requests are not approved yet, okay? But we have to prepare the complex well in advance to be able to assess if we can make it or not. So besides Na61 requesting new ion species, there is ALICE3, which is a new detector being proposed, which requests the highest possible nucleon-nucleon luminosity, which we know that in principle cannot be reached with lead, but probably with lighter ions. And the list of possible lighter ions is oxygen, argon, calcium, krypton, indium, and xenon. So in our working group, we will have to study as well, together with the Na61 ions that I mentioned before, all these lists of ions, and choose one of them. And the one that we will choose will be the one that gives highest nucleon-nucleon luminosity to ALICE3, but that also has the highest mass, because they are interested in a high mass, high luminosity. All right, so, okay, so can we do this straight away? No, we cannot. We have currently some constraints in our injector complex, and I would like to briefly introduce them to you. As I already said, we have just one source. So any new development and operational beams share the same source. Therefore, any studies that we have to do have to be done outside the operational run and with minimal impact on the source performance. Because at the end of the year, we have to always give to LAC lead ions with the highest possible brightness. We also suffer for rather poor beam diagnostic right after the source. So we cannot characterize properly the beam that is coming out from our source. And therefore, we cannot develop realistic LINAC-3 models. So we are always relying on scaling laws when we are giving predictions. And also, this is important because this doesn't allow us to know if we have bottlenecks in the machine. For the moment, we are blind, and we might have actually bottlenecks that we don't know about. And if we could know them by proper beam diagnostic, we could even increase the brightness of our beams. There is also insufficient beam diagnostic after the source in the low energy beam transport line of LINAC-3. Another constraint is that ion species development needs weeks if they are gases. As I said, it's easier to operate gases. 2 months if they are solids. And we need to address what is the stability, what is the long-term operational issues, because in the past, operating other ion species, we found our beam pipe damaged by the impact of these other ion species. And we also need to address safety procedures. Today, we didn't have to have any special safety procedures with the ion species we have operated up to now. But for example, lithium, which is one of the candidates, we know already it has quite a number of chemical hazards to be taken into account, and we are not familiar with. Then we also need experimental tests, because without tests, there is no valid prediction. in terms of intensity and what are the dominant charge states out of the source. Then some ion species require special personal protection measurements because of this neutron generation that increases as the mass decreases, which activates the material. As I said before, LINAC 3, which is a simple control area, access is possible during beam operation, but some ion species or beam intensities are prohibitive unless personal protection is upgraded into this hole. You see, some barriers or some access constraints will have to be put into place when we are dealing with an ion species that brings high neutron radiation and material activation. LIAR has a similar problem because LIAR is an open machine. It does not have a roof. You can climb on a platform and see the machine from the top. So we also know that the operation of some ion species, depending on the intensity and depending on the acceleration of the kinetic energy after acceleration, might bring also serious neutron generation issues. And we have to study them and see if they are compatible with an open roof, which brings straight radiation into the building where there is people operating other things. And some species also might have an impact on radiation to electronics, which will have to be also studied. Then another issue is the electron cooling. So as I said before, we inject 7 times, but in order to make a space for the new injection, we have to bring the injected beam to another value of momentum. This is beam momentum in the horizontal axis as a function of time, as a function we are injected the beam into the LIAR machine, and this is a Schottky image. So this process is achieved thanks to our beam cooling system, the electron cooler, and we will need to understand if our LIAR electron cooler is capable of cooling down the new ions in this available time, 200 milliseconds. And also we will need to understand what is the beam dynamics with the new ions across the complex, because different ion species might bring more issues in terms of space charge and intrabeam scattering than others. Then there are also schedule constraints, because even if we could have 2 sources, we cannot do PPM operation, which is the following. We cannot have lead delivered to, for example, LAC, okay, and then after 3.6 seconds, which is the duration of the preparation of the beam, we cannot produce argon for Na61. This is not possible. Why? Because many elements in LINAC 3 are not pulse, are DC elements, as well as in the transfer line and the injection element of LIAR. They are DC. So we would have to change also all these elements to pulsed magnets in order to be able to pulse to different intensities currents as a function of the ion species every 3.6 seconds. All right. So more constraints comes also from LAC, but this was very well explained by Roderick before. We have to look into, for the new ion species, specific challenges related to higher stored beam energy, higher luminosity. How are we going to collimate these new beams? Is going to be more or less efficient than with lead. What is the machine protection that we need to put in place? The beam loss mechanisms that were mentioned, etc. Is crystal collimation cleaning efficient for the new isotopes, etc., etc. So this will have to be addressed as well. So given the large number of requests after LS3 that we got so far, and given the number of accelerator complex constraints, the accelerator and technology sector saw the need of creating a study group to evaluate the implications of these recent requests from LAC concerning highest luminosity and highest density ion collisions as from RAM5, at the same time as the implications of Na61 requests for light ions as from RAM4. And this is why a working group on future ions was created that I mentioned after the question that you mentioned. And we have a mandate, and the mandate is very clear. So we have to determine what are the current limitations in the complex. I already told you the most important ones. So from beam physics, from radio protection, from source operation, from radiation to electronics, from RF system, from main instrumentation, and deliver a possible list of improvements. One could be, we need 2 sources, and quantify what is the expected performance after those improvements, and propose realistic implementation plans. So you see, NX61 want to see these beams already in RAM4. This is around the corner, and is really the day after tomorrow in our schedule. With costing, so how much is going to cost, and what are the resources we need for putting all this making it real. But not only that, not only we have to study this, we have to exploit synergies with other studies or requests for ions to minimize the overall number of ion species that are required, and to ensure that any proposed implementation does not prohibit possible future experimental requests. I mentioned Na61, I mentioned LAC, but there is the gamma factory, which is also coming with proposing calcium and partially stripped ions of lead. And I also include your isobar collisions proposals at LAC that we are discussing during this workshop. So all these synergies will be studied with this working group. So we have to report to our management, but I don't go into the details. This is boring for you. And what is important is the timelines. So we have some deliverables that have to be finished along run 3. And in particular, what is affecting Na61 has to be delivered already so answers to any Na61, because they want to run in RAM4, have to be delivered already at the end of this year. For LAC, we have a bit more time because they will come in RAM5 or RAM6 if they are approved. Alice 3 is approved. So we can complete everything related to LAC by the end of 2025. So this is our timeline. Okay, I will skip this slide because it just tells you to which we are reporting. And I would like to present you what is the current status of the studies. So I have presented to you what are the limitations, but I already told you that we have been working on this since 2019. And this is the situation for LAC. So LAC is requesting this high luminosity with the highest mass possible ion species. And what you see in this plot, it is as a function of the ion species that are possible candidates for LAC. This is the number of nucleons per bunch that we can provide. And there are 2 colors here. The red color is the initial estimates that were given some time ago by a working group working for a high luminosity LAC project.
Reyes, you have 1 minute left.
Yeah, and you see when we started this working group that I just mentioned before, we realized that the luminosity was much smaller than what had been proposed by this working group. So we had well, this was really a finding that was very worrisome for ALICE 3. So we had to propose during studies in this working group additional measurements, additional possibilities on how to improve this luminosity. And these are the proposals that we are studying in this working group, like new strippiness scenarios, new charge to mass ratio optimization of the different ion species, and so on and so forth. This I will also skip because that's the performance that for the moment we can promise to LAC without studying in detail the new species. What is the situation for Na61? So we are studying this for ion species, and we have to choose in between helium, lithium, and boron. And we are doing radioprotection studies and also studying what are the chemical hazards and what are the difficulties in manipulation in the source, etc., in order to choose which one will be the easiest one to operate. Concerning oxygen, this has been already discussed by Roderick. So we have a concrete plan for oxygen will come in 2024. And in argon, so we already operated argon for Na61. LAC could also benefit from it because it's one of the candidates. So this we know how to do. Xenon, we also did in 2017 for ALICE, for collisions in LAC and for the Na61 experiment. So this isotope we know how to handle, is not a problem. So I just come to my summary. So after the several possible ion species that have been requested after LAC and the actual number of accelerator unknown and constraints, we have this working group that is trying to assess feasibility. And this working group has to include synergies with other potential programs. Therefore, if INT requests new ions, and I saw you here the table of in this publication where you are also interested, as you can see, in the same ion species that I have shown you for LAC, we can explode these synergies and make something that can be also useful for ANT. But, and the but is here. Whatever program you would like to propose, it has to be approved first by the LAC committee, and it has to be approved by the research board. So the message here is that we are, of course, we will take into account your proposal, and we will study this proposal within the working group using this momentum. But for serious studies, we will need your program to be approved by the relevant bodies at CERN. Otherwise, we can just give you estimates. And this is my last slide. Thank you for your attention.
Thank you, Reyes. Questions? So while we're waiting for questions, I know I have a question. So how would the run of oxygen, assuming everything goes well, how would that affect future runs? Like, would it be more likely that we could get an argon run afterwards if oxygen goes smoothly?
So the oxygen run that will take place next year is a very interesting one, because during 2024, the ion complex will be able to prove that we can run two species in the same year. In the first half of the year, oxygen; in the second half of the year, lead. And this opens the possibility in the future to do the same. The first half of the year, we can run argon or xenon or any species like Na61 is requesting. And in the second part of the year, we can come back to lead, which is the preferred isotope for the moment for LAC. So that's the importance of oxygen. We will demonstrate our capability of running 2 species per year.
Cool. Other questions? Yeah, Janelle?
So we have done the Xenon 129. How much it takes to do other isotope of the Xenon? Like it's just straightforward thing to do.
So we could have another isotope, as I said before. We could put it in the source, probably will be more expensive, but it's not an issue, provided the charge over mass ratio fits within our accelerator constraints. It should not be a problem.
So the constraint of charge mass ratio, what's the constraint? Like what's the range? What do you mean by that constraint?
Well, our LINAC accelerator, because you see, it can only accelerate to a given kinetic energy, and is fixed. This value is fixed. So we cannot reach. So we cannot operate any ion species, any charge to mass ratio, if it does not fit the final kinetic energy that is fixed by the LINAC 3 machine. This imposes some constraints, together with the amount of X-rays that we might generate when we, according to this mass to charge ratio also. So
it means a neutron rich, like really neutron rich species may not work.
I don't know. I would not. I need exact numbers, and then I can answer you the question. We know we have some limitations in the mass to charge. So some of them we cannot operate. We can operate mass to charge ratios of the order of 0.25, 0.3, you know, this order of magnitude. But okay, I would need to know the exact value to tell you.
John, did you have a follow-up comment or question on that?
I was just going to expand a little bit. It depends also on the charge to mass ratio affects also the RF frequencies in the various machines you need to stay with. So a very neutron rich isotope might get more difficult. And the energy in the LHC would be, the energy per nucleon would be a bit less, of course.
Yeah, so
There
this
are quite a few things to be checked in the whole chain. I guess you agree.
The bunch free, your neutron, whatever this process was talked earlier, like the background, probably that depends on the binding energy, right? I mean, I don't know if you have something that
The boundary pair production.
Yeah.
Its main dependence is on the charge of the nucleus. It goes as the 7th power actually. So for xenon, it's quite a bit less than for lead.
Okay.
Right. Well, let's thank Reyes once again for the next. And then we have coffee.
Excellent.